All right, I will begin with a word of prayer. I will start. Heavenly Father, we thank you for this day. I thank you for these students. I ask you to bless our time together. Help us to glorify you, what we do, and just understand a little bit more about your creation, Lord. In your name I pray. Amen. So yes, I've heard the top hat is troubling some of you. I'm sorry about that. Any questions about anything particular in the homework? Anybody? No. All right, so last week I talked about the laws of logarithms, right? And what were those laws? We had like log base A of, let's say, x plus log base A of y equals log base A of xy. All right. And we had log base A of x to the power p equals p times log base A of x. And we also had log base A of x over y equals log base A of x minus log base A of y, right? These are the laws of logarithms, right? Now, here we assume that x and y are greater than 0 and a not equal to 1 is positive, right? That's the the assumptions when you write these laws, right? And I never explained to you why these are true, right? But let's just take a couple minutes here and try to, I'm going to try to prove these to you, and let's see if we can do that, all right? So now, all right, so what do we know? A few things. All right. Let's see if we can do this. All right, so it's a little bit sneaky, all right? The proof here is actually quite a bit sneaky, but here's the proof that we'll use. And I don't do many proofs in here, so, right? But here's one. It's pretty rare. If x and y are positive, right? Think about this. That means we can find, let's say, u and v such that x equals a to the u and y equals a to the v. Do you agree or disagree with that? I mean, could you tell me what the u and v we could use are? Like u equals what? I could use u equals, log base A of x, and I could put v equals to log base A of y, right? Because then, if you check it out, right, a to the u is what? A to the log base A of x, which is, by the way, x again, right? Okay, so that's fine. That's a step we can definitely make. We can find a u and a v such that x equals a to the u and y equals b to the v. So then notice that if we do a to the u times a to the v, what do we get? What's the law of exponents? It says what? That's a to the what? A to the u plus v, right? But what does this mean? This means that the log base A of x times y, right? This is x, that's y. It's equal to the log base A of a to the u plus v, right? But by the definition of logarithm, what's that equal to? That's equal to u plus v, right? But what is u and what is v? Well, u is, see right here, log base a of x. And v was log base a of y. So there you go. There's the proof, if you will, of the first law of logarithms. The power property, so that's let me call this number 1. That proves number 1. Here's number 2. Here's number 3. Let's do number 2. For number 2, let's look at log base a of x to the p, right? I can follow the proof I was just doing. What did I say x was equal to? A to the u, right? So I can rewrite that as log base a of a to the u to the p power, right? Which by laws of exponents is a to the up, right? And then that, by definition of logarithm, is p u log base a of a. What is log base a of a? We talked about this last week, right? Log base a of a is just 1 again, right? By definition. And what's u? Well, that's p times u. What was u? U was equal to log base a of x, right? So there you go. That's the proof of the second law of logarithms. I think that these proofs are more difficult than the other ones I've shown you this semester so far. Like pretty much the only proof I've really showed you up to this point was what? Like quadratic formula, or perhaps completing the square, or basically we derived the quadratic formula by completing the square. I think that proof is much more front and central in this course, because I expect you to be able to repeat that proof. This proof I don't actually expect you to be able to repeat. This is something I would want math majors to be able to like reproduce for me, but I don't think it's an appropriate proof to ask of you guys. So I'm just kind of sharing it with you for the sake of completeness here, not for the sake of you like repeating it back to me or anything like that, okay? I just wanted to show you it's not magic, that these are just straightforward logical consequences of the ways, you know, our known laws of exponents and how we define the logarithm. How did we define the logarithm? Remember our definition? Definition, y equals a to the x implies what? Log base a of x equals to y, right? So that's essentially the definition of the log base a, is that. And there are two sort of guiding equations that I always think about, namely log base a of a to the x equals to x, and a to the log base a of y is equal to y, right? So these, we always keep those in mind as we're working. So any questions? Because we've been, you know, tinkering. You're fine. We've been tinkering with this stuff for about a week now, you know. So I hope you have made progress on your homework. You got stuck on something, maybe you can ask about it, whatever. Anybody?
I might have something to give you a second.
I mean, I can just dive into the homework and work problems, but I'm giving Savannah a second here at the moment, so. You're okay.
When you put a and then log a up here, the second one here,
Yeah.
what is the point in even having that? Like, because a to the log a is just a, right?
Well, a to the log a is not just, I mean, this is the composition of functions. So I have the exponential function composed of the logarithm function acting on y.
So y is also exponential.
So here y is just a positive number. Here x is anything.
Okay.
So unfortunately, I'm teaching 4 different sections of this class, so it's hard for me to remember which homework problems I have worked for you guys. You'll have to stop me if I start working one we've already worked before, okay? What's that?
Can we do some graphing?
Yeah, we can do graphing, of course. Which one would you like to do? Was that your question, Savannah? Graphing? Was it one of the log ones or one of the exponential ones?
I think it was.
Here, I'll start out real easy. Number 33. Here we're looking at y equals log base 3 of x, right? How do you graph log base 3 of x? So I suppose the most simple thing to do is just to make kind of like a table of values. If you really don't know, and this is something we really should have memorized at some point soon, but you know, here we can look at x, we can look at log base 3 of x, and there's some things we should have in mind, of course, like number 1, if you plug in 1, you get log base 3 of 1. That is equal to log base 3 of log base 3 of 3 to the 0, which is 0. All right? So log of any base of 1 is 0. And also another really easy, like low-hanging fruit here is 3, right? Log base 3 of 3 is equal to 1. So that gives me 2 points on the graph, right? I've got like 1, 0, right? And then also 3, 1. And I don't know, let's look at like, we could look at, you know, 1/3 if you want. What would 1/3? That would be log base 3 of 1/3, right? Which is 3 to the minus 1. So log base 3 of 1/3 is minus 1 because 1/3 is 3 to the minus 1. All right, and so 1/3 and minus 1 is you know, round about here.
Why would it be 3 to the minus 1?
Because 1/3 equals 3 to the minus 1. So it's just that.
So if it was 1/2, it'd be 2 to the minus 1?
That is true, but that is true. 1/2 would be 2 to the minus 1. And if we were to calculate log base 3 of 2 to the minus 1, it equals nothing particularly nice. You know, the base has to match the 3 here.
Oh, okay.
I know you're just asking like a more general question about like fractions, right? And that's all good. Now, if we were to plug in a 9th, what would happen? Like, what would a 9th be? A 9th is 3 squared. 9 is 3 squared, right? So this is log of 3 to the minus 2, which is minus 2. So like by the time I get to 1/9, I'm down to minus 2. You know, and this just gets worse as you go to closer and closer to 0, right? It gets more and more negative. So the graph of log base 3 looks something like that. Y equals log base 3 of x. What I do for 1?
For x equals 1, you should change the x.
Oh, well, yeah, I'm just explaining that the reason, I mean, I claim that log base a of 1 is equal to 0, but part of the reason for that is this. 1 is a to the 0, right? And right, I mean, then it goes back to that's log base a of a to the x is x again. So, you know, we could think of log base a of 1 being 0 as being the case x equal to 0. Of course, I would also encourage you to not think, I mean, like, you should just know when you come up against, like, if I come up natural log of 1, you should just be like, oh, that's 0, you know? Just like if you come to e to the 0, you should be like, oh, that's 1. Same, by the same token, right? These are things we should know. So there's the graph. Yeah? Now, I think this had like, this is an ABCD question, so it's kind of fairly obvious what the choice is, I guess. But anyway. Other questions? So before we got to this material, what we were doing, we were finding the formula for an inverse function, right? Maybe we should try one of those examples now that we have a little bit more algebraic tools to work with, right? Like here's an example. I guess this was example 1 for today. Example 2. Suppose f of x equals 3 plus 2 to the x minus 7. Is f 1, 2, 1? If so, find formula for f inverse of x. So how can we check if the function's 1 to 1? What do we do? How do we check? There's two different approaches we had, right? We could either go graph it and look for the horizontal line test, right? Or we could use the algebraic method. Which way do you guys want to do? Algebra or graph? Algebra? Okay, so algebra, I promoted putting f of a equals to f of b. That's what I did, right? And so what's f of a here? It's 3 plus 2 to the a minus 7 equals 3 plus 2 to the b minus 7. Now we can subtract 3 from both sides, right? So this implies that 2a to the minus 7 equals 2b to the minus 7, right? But then what could we use? We could use the 1-to-1 property for the exponential base 2, right? By the 1-to-1 property for 2 to the x, this implies a minus 7 equals to b minus 7, 1-to-1 property for y equals 2 to the x, right? And then that gives me a equals to b. And so, thus, f is 1, 2, 1, right? Graphically, if you had gone the graphical route, what does the graphical route look like here for the 1-to-1 proof? Because graphing this function is also an important problem for us, right? We'd like to be able to graph it. So here's the graph. The graph is just this. We're shifting up by 3. And we're shifting right by 7. And it's 2 to the x, so it looks basically like this. There's the graph. Does it pass the horizontal line test? It sure does, right? This point right here would be like 7, 4, for example. So it passes the horizontal line test, therefore it's 1-to-1, right? Okay, that's lovely and all, but how do we actually find the formula for the inverse function here? What would you do? How would you find the formula for the inverse function this time? What was our methodology? What do? We start with, it's a 4-step process, right? 4 steps. Step number 1 is what, right? What? Number 1, we write y equals f of x, right? So step number 1, y equals f of x. Here f of x is 3 plus 2 to the x minus 7. Step number 2 was to solve for x Now, solving for x here is going to require us using the algebra that we've just, we're just starting to learn, right? How do you solve for x here? Move everything to the other side. I like that. So y minus 3 equals 2 to the x minus 7. Now, how do we get rid of the 2 to the something function? What do you do? We take, so the natural enemy of the exponential is the logarithm. So if you have an exponential, you want to get rid of it, you take the log of both sides. Log base what? Log base 2. So log base 2 of y minus 3 is equal to log base 2 of 2 to the x minus 7. But log base 2 of 2 to the x minus 7 is equal to x minus 7. Then one more move, and we've isolated x, right? X is equal to 7 plus the log base 2 of y minus 3. So that right there is, as I called it, very intellectually when I introduced this idea, stuff in y. There you go. This is the stuff in y I talked about. Right? So that altogether, you could say, is equal to f inverse of y. Now, we're not after f inverse of y right now. We want f inverse of x, right? So final move here. That was step 3, by the way. Step 4 then was to switch y to x. So I have f inverse of x is equal to 7 plus log base 2 of x minus 3. So there you go. That's the formula for the inverse. What's the graph of the inverse function look like? If I was to foolishly try to add the graph of the inverse function to this picture over here, how does it go? I mean, I can try to do it down here. The graph of the inverse function, we've got a vertical asymptote at at x equal to 3, all right? And it gets, poor planning on my part. I should have put this axis. Yep.
Question, you just said that that's a vertical asymptote, right?
Yes.
So on the problem before that, I guess you have a vertical asymptote at 7?
Oh, this one?
Yeah.
Oh, there's no vertical asymptote here. This is just a dotted line I drew. So what I should say is more like this. This vertical line, let me make it not dotted. Okay, this vertical line, x equals to 7. All right, let me try to make a sentence here. That vertical line, x equals 7, is to the graph y equals 3 plus 2x to the minus 7, as the y-axis is to the graph y equals 2 to the x. So this is like if I was to draw an axis that's vertical with respect to the given function, that plays the same role as like if I have the plane y equals 2 to the x graph, looks like this, So the y-axis, in that sense, I drew that. It's not a vertical asymptote, but I think if I talk more, I'll just make it more confusing. Let me shut up. So here, we have a genuine vertical asymptote of x equal to 3 here, and the whole thing shifted up 7, right? So, like, in the same sense, I was just this here is not an axis, right? But this behaves for the logarithm in the same way that this behaves for my previous example, in the sense that, well, yes, the horizontal asymptote at 3 for the function becomes a vertical asymptote at 3 for the inverse function, and anyway, it looks something like this. And if I could do that properly, you'd see that the red line is the reflection of the blue one across the line y equals x, but, you know. Sorry, I'm not talking about one problem. I'm talking about a couple different problems at once here, right? Because the problem I stated was just to find the formula for the inverse function, right? So actually before that we did a more basic problem, which was, is the function one-to-one? We answered that question. That's a single question in and of itself, right? Yes is one-to-one. Once we knew it was one-to-one, we can find the inverse, right? And we did this algorithm, we found the inverse. There's the formula for the inverse. And then while I was at it, I decided to go ahead and graph the inverse, because I think that's also an interesting problem for us to look at. How do you graph a logarithm that's shifted? Well, like this. So did I answer, did you have another question, or?
It was mostly on inverse stuff.
Mostly on inverse?
Earlier in the week.
It's fine, we can talk about inverse stuff, just ask me. It's fine.
I think it was like 7.
Number 7? Sure. All right, so number 7. Let's talk about this. This is example 3 for us, I guess. This is number 7. So we're given f of x equals, for me, it's the square root of 3 plus x, right?
Oh, mine was a negative.
A negative?
Oh, well, square root of -1 plus x. That's the one.
You got square root of -1 plus x. And then what's it say? X is something,
1.
x greater than or equal to 1?
Yep.
And it wants you to find the domain and range of the function and determine if the function's one-to-one and find the equation of the inverse function, I guess. Right. I will. Okay, so you got A, B, C choices, right? So here's the deal. If the function's not one-to-one, you can't find the formula for the inverse, right? So if the function's not one-to-one, you choose option C, right? Now this here, I believe, is one-to-one. So listen, so the way I would graph this would be like this. This is x squared of x minus 1, right?
Yeah.
So we can take the graph of square root, which is this, right? And then we just shift right. Shift right. Well, vertical line test just tells us it's not it's a function. That doesn't tell us it's a one-to-one function. So, but heart's in the right place. Just change that vertical to a horizontal. Then we got then we've got something to work with. So, indeed. So if we look at this, any horizontal line cuts through the graph at just one point, right? So passes horizontal line test, right? Passes H-line test. Now we need to find the formula for the inverse, right? So let's go through our 4-step program. Step number 1. Y equals the square root of x minus 1, right? Now step number 2, you got to solve for x. How do you do that? How about we square both sides, right? Square the equation. So we get y squared, square root of x minus 1 squared. Then what? Well, square root of x minus 1 squared is x minus 1 again, yeah? And then we can solve for x. X equals to 1 plus y squared, right? That is my quote-unquote stuff in y. That is what we have right now. You know, I would say that this is f inverse of y, but we don't want f inverse of y. We want f inverse of x, I think, for this question, right? So f inverse of x is equal to 1 plus x squared. Now, and it says choose the correct graph below. The solid curve shows the graph of f, and the dotted curve shows the graph of f inverse if applicable. On my printout, I can almost, I'm struggling to see the dotted curve. Like, check this out. Can you see the dotted curve on my printout?
No.
No.
Oh, barely. Almost.
Yeah, I mean, if you really,
Yeah.
it's like one of those magic puzzles, you know, just kind of like, just got to like unfocus to the right. I don't know. Anyway. Okay, so I will do my best when I make the next test to not include a dense grid to put the graph over so you can't see anything, you know. Real professional here. Anyway, I digress. So we were asked a couple other things, like what's the domain and the range for the function? Can you tell me that? What's the range of f? What's the domain of f? The domain is what? It's just everything to the right of 1. So the domain is 1 to infinity. You guys see that? That was essentially given to us because they told us x was greater than or equal to 1. So the domain is imposed on us there. And then the range is what? Now the range, you're right, is 0 to infinity. See, the range is 0 to infinity. Although it depends on what we're talking about. If we're talking about the function, that's the domain and range. But remember that the inverse function, it flips it over, right? So down here, the range of the inverse function is 1 to infinity. And the domain, and here's where you got to be careful, guys. What's, you know, if I cover up everything else here, right? If I just go over here and I say, you know, h of x equals to x squared plus 1, what's the domain of that function? What would you tell me? I hope you would tell me it's all real numbers, right? What? Everything, right? So, the domain of everything. Because it's inverse, right? Then it can on obligation has the function. It's inextricably high the function has the name of the function. So the domain of inverse is 0 to infinity. power P is equal to C means what? That means log base A of C equals to 0. And I mean, if you have a ring of a f names log, you take A both sides. See that? So I have log base A of A to E equals log base C, right? This by B equals to log base A. So if you get out the change you can take log exponent. This one, so if I take log base so it's to back x cubed log s for 3 right? So this is equal to log s 6 for 40. Now, I'm saying that all stuff is red. Just if you're probably seeing what she saw, yes, this is the way you think about it, right? I don't think about it. Just take the original equation side.